Hello, my fellow physicist. Let's learn about motion. All right. So, speed and acceleration. We're surrounded by moving things from a car moving in a straight line right down, like the drag racers do, uh, or even a satellite that orbits and moves in circular motion. Circular motion. Uh, Objects move in a variety of ways, and you've learned now about frame of reference, and oftentimes motion and movement, how we describe it, is based on how we see it from our point of view, right? Which is what makes astronomy and seeing stars so odd. To across the sky in these vectors. Well, in everyday life, motion is so common. It seems to appear very simple, right? But in fact, understanding motion requires some new and advanced ideas. So how do we know when an object is moving? All right. And you learned that an object is moving if it changes position. Good. You were thinking of that, weren't you? All right. So today we're going to see just how do we measure that change in position, and what do we call it when that position is changed? Well, there is speed. And what's the difference between speed and acceleration? Before we get into all of that, what's going to be encompassed upon this lecture, let's go over some groundwork first. Today, you'll be able to describe and compare speed and velocity and what the difference is between speed and velocity. Those are two things you want to know the difference between. You'll also be able to perform calculations. We'll just do a couple small examples with measured data, which means you'll have to remember what meters, miles per hour, meters per second. It's always going to be distance and time and speed. So calculations with measured data to find velocity and speed. And what's the difference between speed and velocity, as we set up here. Tomorrow, that is Wednesday, you'll be able to create and analyze a graph of time versus distance. So today is only slides 1 through 17. And I'll probably go through pretty quick because I just want to have an introduction here, but you have this PowerPoint, which you can go through again, or even this lecture, which you can go through again. All right. So I don't know if my picture is in the way on this slide or not. I can't tell. But here are some physics quantities and some particulars you want to know, okay? So first, there are vector quantities. Say vector, right? So this is a quantity with both magnitude and direction, okay? When we say magnitude, all we mean is like size, small, medium, large. What's the magnitude of that Diet Coke you got there? 32 ounces. Wow, that's a good size medium, isn't it? That's pretty good magnitude. Mine's 44 ounce, much greater magnitude, right? It's magnitude. That's all magnitude is, how big something is. It's a numerical value. But when you put a direction, now it's a vector, okay? Versus scalar. So scalar, S-C-A-L-A-R, it's hard to see that. Say scalar. Right. So scalar, quantity with magnitude only. Got it? So all we're interested in is size and value. Wow, see how fast that was going? Who cares what direction? It was just traveling, right? So vector and scalar. In physics, this is an important difference to make, okay? So here are some examples. Displacement is a vector. Okay, so let's think of a baseball field. Someone's hitting the ball with their bat at home plate. They might run to first base and second base. So they've traveled a scalar distance of 60 meters plus 60 meters is 120 meters. All right, So they ran to first base was 60, and they went to second base, another 60. So when you add that, they'd win a total scalar distance of 160. But how far are they from home plate? Well, a straight line between home plate and second base would give you a displacement that is much smaller than 120, right? Because you kind of went in a curve. You went out and then came back in. So the distance between home and second is shorter and than the actual distance traveled to get there. It's kind of like taking a scenic route. That's the difference between displacement and distance. We'll see some more of that. Another scalar quantity that is not specific, it's just numbers, is speed, miles per hour. Didn't say where you were going, didn't say for how long or what the distance, just a speed at any given moment versus a velocity. When you say velocity, velocity is a vector value that has direction, traveling 60 miles per hour north. A vector is 60 miles an hour, or let's say a surfer, all right, riding a wave at about 30 miles per hour toward the shore. Toward the shore gives it a direction. Surfing toward the shore. That's a vector quantity. Speed is just speed. Velocity entails a direction. Then there's time and acceleration, momentum, mass, force, energy. These are not opposing each other. They're just some values you might see. The ones we'll be working with are primarily going to be these that I've just mentioned. Distance and speed are two scalar quantities. Displacement, velocity, and acceleration are going to be vector quantities. We won't play a lot with them, but you do want to understand the definition of the distance, that velocity entails direction. Displacement entails shortest distance as a crow flies between two directions, even if it took you a forever distance to get there. Here's some examples of vectors. Vector A, we're going to label this one A. You can see this arrow. This vector quantity, because it has an arrow on it and it stops right here, is a vector because it has a defined distance. They're going the same direction, but they have a different magnitude. So A is much bigger than B. So vector A is not the same as vector B. Example 2, vector A, same, but vector B now seems to be over here. It's not parallel. So vector A and vector B have the same magnitude. They're the same size, but they have a different direction. Therefore, they cannot be called parallel or the same vector. In this last example, you have vector A and vector B have the same direction, they're parallel, and they're the same size, magnitude. Now we can say vector A equals vector B. We might be tempted in example 2 to say that vector A and B are the same, but we couldn't call them the same because they only have the same magnitude. They're going different directions. So direction in physics is a very important thing. All right. So vectors are often represented by arrows, and the length of the arrow represents the magnitude, how far, how fast, how strong, etc., depending on the type of vector. So let's practice and see if you know the difference. All right. Here's a quantity, 5 meters. M stands for meters. Is that a vector or scalar? Is there a magnitude? 5 meters. Is there a direction? Nope. Therefore, it is scalar. Okay. 30 meters per second. That's a speed. East. We added direction to the speed. That makes it velocity. Which side of our chart had velocity? Correct. Vector side. 5 miles north. Again, we have a distance, but we also have a direction. Vector. 20 degrees Celsius. What do you think? Scalar. 256 bytes. That's a measurement of information on a computer. 256 bytes, scalar. 4,000 calories, scalar also. If you want to review that, go back to the previous slide. So let's go back to a couple of these concepts, distance versus displacement. How far an object travels. We'll let D represent distance. So when we talk about distance, it does not depend on the directions. You might, well, let's just say me, if you don't mind. I could throw a rock pretty hard and I will hit the highway because I live right off the highway. My distance to the highway is probably about 100 yards, like the length of a football field. Actually, not even that long, probably 50 to 75 yards. That's the distance I would be displaced. But to actually get to that point, I have to go out my driveway, down the road, take a left, go all the way up, not even half a mile, but almost half a mile, then take a left, go a quarter of a mile, then come back for that 3/4 of a mile, come around. I'll have probably traveled 0.71, about 1.5 miles to get right over there. Well, right over there. 1.5 miles to get right over there. So I can't drive through my neighbor's house and the fence and down the ditch into the highway, right? You get the idea of the difference between distance and displacement. Distance is how far an object actually travels. I would travel 1.5 miles to get there. I've only been displaced 75 yards because it's right over there. So if you walk 20 meters west and then 10 meters east, what is your total distance? Think about it, pause. So let's remember distance versus displacement here. So a triangle, you got to remember this so you don't get thrown off. Triangles mean change. What do triangles mean? Change. So X, in this case, is the unknown. So a change in X, that is displacement, is where you are in relation to where you started. I started at my house, and where am I going to be in the end? I've been displaced 75 yards. How far did I travel? 1.5 miles to get there. Does depend on direction, okay? So distance is only how far you travel. Displacement depends on direction. Whoops, I got a typo there, direction. So let's go back to our question. If you walk 20 meters west and then 10 meters east, what is your total displacement? All right, let's go back now and look at these again. First, I asked you 20 meters west, then 10 meters east. What is your total distance? You would add them together. 20 plus 10 is 30 meters. You traveled a distance of 30 meters. 20, U-turn, came back 10, that's 30 meters traveled. What was your displacement? Well, because you came 10 meters back, right? 20 west, 10 meters back east, you've only been displaced 10 meters. So you get the difference there. 20 minus 10 is 10. All right, if you didn't get that, rewind this portion and watch it again. But again, you traveled 20, you came back 10, so that's 20 plus 10 is 30 is what you actually traveled in distance. But where you started and where you ended up, it's only 10 meters. So calculating speed. That's distance traveled, D, divided by the amount of time it took. Okay, so calculation for speed is S equals D, that slash means divided by. So you put the number in, the divided symbol on your calculator, and you put in the time. You may use calculators. So S equals D divided by T. So the units for speed depends on what you're talking about. I could ask you how many centimeters to Joplin. That's pointless. I don't care how many centimeters, and one, it'd probably be something like in the thousands, hundreds of thousands of centimeters. We don't travel in centimeters, right? We measure distance like that in miles. Miles makes much more sense. So whether it's miles per hour, that would be a car. If it's kilometers per hour, you might be in a jet. Snails, centimeters per second. Why? Because snails are slow. Do you really want to measure how far a snail goes in 1 hour? I don't. So clock it for 1 second. Stop. So you got a few centimeters in 1 second. And now you have your centimeters per second. can always multiply that up if you want to find out how much you went in an hour. Falling objects, how many meters it fell per second. Okay, so calculating speed is, again, distance divided by time. If I travel 100 kilometers in 1 hour, then I have a speed of 100 kilometers per hour, right? If I got 100 kilometers and it took me an hour to do that, then the speed I traveled was 100 kilometers in that hour. So you need that time element, time. If I travel 1 meter in 1 second, which is about one big step, takes about a second to make a big step, then I have a speed of what? 1 meter per second. And that's the way you say that. It's a kilometer per. That per means divided by. So you'll have, after you're reading and looking at some other sample problems, you'll have one question to answer. So speed is usually not constant. If you're going to Joplin, you get there in an hour and it's 60 miles away. You could say you went 60 miles per hour. Likely, you went 40 miles per hour through town to get to the highway, and then went 80 miles an hour on the highway, and then it had a couple slowdowns and stops, so that your average speed was 60 miles per hour. So cars stop and go regularly. Runners go slower uphill than downhill, but what we're usually interested in is the average speed. So that's the total distance traveled divided by the total time it took. Instant speed or instantaneous speed is a little harder to measure, and usually only the police do that with a little ray gun. Bing! Clocked you. So here's a question. If you travel 250 meters in 10 minutes, how fast did you go? 250 meters in 10 minutes. What's our formula? Look back if you need to. Speed equals distance divided by time. The distance was in meters, so meters per minute. So we're going to want a meters per minute. It's going to be A or D. Those are your 50-50 shot there. And so when you divide 250 by 10, you take away the last 0 and you're left with 25. You're going 25 meters per minute. That's the speed. Again, if you didn't understand, rewind this again. So the formula you should have written down from notes is speed equals distance over time. The distance traveled was 250 meters. The time was 10 minutes. So 250 on your calculator divided by 10 equals, and you're going to get 25 meters per minute. All right, velocity. Last thing real quick. So velocity is speed also. So we've learned to calculate and we've reviewed speed. You'll see this in the readings and the videos, and we'll have some more examples. But now we're adding what? Direction. So whenever you see direction in the question, you know that I'm asking for velocity and not just speed. So here's an example. An airplane is moving north at 500 miles per hour. A missile moving towards you at 200 meters per second. These are velocities. Why? Because these are two different ways to give direction. You can say one of the cardinal directions, north, east, south, west, or you can say towards a particular point of reference, such as moving towards you. That would be a direction. That's what qualifies it to be called velocity. So what is the difference between speed and velocity? Okay, you're going to answer that on the do now or the exit ticket for tomorrow. That concludes this. Hopefully, we've now seen that we have 3 objectives of the 4, or 2 of the 3 objectives. Can you compare speed and velocity? Can you perform a calculation given the data to find velocity or speed? If you can't, you might watch this video again or give yourself some time and go ahead and do the reading. And then come back and I put, of course, a problem after the reading for you to practice on. I'll go over those answers later. All right. Have a fantastic day.